Hi folks. Today we're going to learn about particles and nuclear reactions. But first we need to talk about what a nuclear reaction is. A nuclear reaction is some sort of change in the nucleus of an atom. But why would that change occur? Different isotopes have different stabilities, and some isotopes are radioactive. That just means that their nucleus decays and releases particles or energy as it decays. So the reason this happens is because to be stable, a nucleus needs a kind of an ideal ratio of neutrons to protons. Remember, protons are positively charged, and we've shoved them all very close together in a nucleus. So you need some neutrons in there to kind of hold everything together because you couldn't put two protons right next to each other. But you can't have too many neutrons either. That also makes a nucleus unstable. So there's this ideal ratio. And if the ratio is too far from ideal, the nucleus is unstable and it decays to increase stability. Throughout the universe, matter is always trying to achieve its most stable state, where it takes least energy to maintain its state. So, looking at particles that are emitted, or types of energy that are emitted in nuclear reactions, the first type of particle that's emitted in a nuclear reaction is called an alpha particle, and we represent alpha particles with this Greek letter alpha. An alpha particle is really just a helium nucleus. It's got two protons and two neutrons. And so there are two different ways to represent it. Either you can write it as a helium nucleus with two protons, so there's a 2 in the bottom left corner, and the mass number is 4 because 2 protons plus 2 neutrons equals 4. Or we can write the same symbol with the Greek letter alpha with a 4 in the top left corner and a 2 in the bottom left corner instead of the helium element symbol. This is a large particle. It's relatively slow moving compared to the other particles we're going to look at. And because it's large and slow moving, it's easy to block this radiation. So paper blocks this radiation. Skin blocks this radiation. It's easily stopped. Sometimes students think that because it's blocked by paper and skin, this type of radiation is not hazardous. It's incredibly hazardous. It just depends on where the radiation is. If it's outside your body, you are reasonably safe because your skin is going to block the radiation. But if it gets inside your body, if you ingest it, then you're in big trouble because your body is going to absorb all of that radiation, and because it can't escape, it can't pass through the lining of your stomach. It's going to get absorbed by the lining of your stomach. The next kind of particle we're going to look at, this is the Greek letter beta, so we call these beta particles. And this is an electron that comes from the nucleus. That may seem weird to you because there are no electrons in the nucleus. However, an electron can be produced as a neutron decays into a proton. So if a neutron converts to a proton, an electron is produced in that process, and it's a high energy electron, so it's ejected from the nucleus. It doesn't just kind of stay in the electron cloud around that atom. Like the example for alpha particles, we can write this as an electron, so a lowercase e to represent electron, or we can represent this with the Greek letter beta. Both are correct. But of course, electrons do not have a mass, so we write a mass number of 0. And we use -1 for the atomic number because of how, you'll see later when we balance nuclear equations, it has that effect on a nuclear reaction because a proton is going to appear at the same time that this beta particle appears. This is a smaller particle. Electrons are very small compared to 2 protons plus 2 neutrons, and it's moving a bit faster, so it's a bit more penetrating in terms of radiation. And so aluminum or wood, you need something a little more dense, a little more substantial to block this type of radiation. There is another type of beta particle, and that's called a positron. It's actually the antimatter counterpart to the electron. So if a positron and a beta particle meet up to each other, they annihilate each other, and a large quantity of energy is produced. Because this antimatter counterpart actually has a positive charge, not a negative charge. It's the same size as an electron, same sort of properties as an electron, except it's positively charged instead of negatively charged. And so we do write the symbol differently to accommodate that. Because when a positron is produced, it's because a proton has decayed to a neutron, and therefore the number of protons in the atom decreases. Like beta particles, positrons are blocked by aluminum and wood. The next kind of particle that's released in a nuclear reaction is called a gamma ray, and it's represented by this Greek letter gamma. And a gamma ray is really a high energy wavelength of light. It does not have any mass. It is pure energy. And it's even more energy than X-rays. It's beyond X-rays on the electromagnetic spectrum. Because this is a high energy wavelength of light, it takes a lot to block a gamma ray. It takes lead or thick concrete to block a gamma ray. Gamma rays The last kind of particle you might see in a nuclear reaction is a neutron, and we've been talking about neutrons a lot in the last couple of sections. Neutrons are used to induce fission reactions, and we'll talk about what fission reactions are in just a moment. And neutrons are also often given off as a product of fission. These are very high energy particles. As we know, neutrons have a mass of 1, but they don't affect the atomic number, so we write that as a charge of 0, not charge. Notice that gamma rays have no contribution to the atomic number of the element and no contribution to the mass number of the element. Gamma rays are often given off alongside other types of radiation particles as energy. Lastly, we have the neutron, and we've been talking about neutrons a lot in the last few sections. Neutrons are found in the nucleus. They contribute to the mass, but not to the atomic number of an atom. And these are used to induce fission reactions, so kind of man-made nuclear reactions in a nuclear power plant or whatever. We're kind of bombarding isotopes with neutrons to make the nuclei of the radioactive material even more unstable so they decay right away. And then neutrons are also often produced in those reactions, so it's kind of self-sustaining. Once you get the reaction started, you have a chain reaction where more neutrons are given off to cause more particles to decay. Neutrons are incredibly high energy from these sources. And in fact, neutrons will pass through lead and they will pass through concrete unless they are somehow slowed first. And of course, nuclear reactors are built with methods to slow the neutrons down so that the big concrete towers lined with lead can block those neutrons from escaping into the environment. So let's look at how these types of nuclear particles appear in different types of nuclear reactions. The first type of nuclear reaction we're going to look at is called alpha decay or alpha emission. And not surprisingly, this type of decay produces alpha particles. That's how you can identify what they are. So again, to remind you what an alpha particle looks like, it can be written as a helium nucleus or as an alpha particle. And this type of reaction happens naturally with heavy radioactive nuclei. So something like uranium-238 just naturally is unstable, naturally decays over time into thorium-234 and produces an alpha particle in the process. So you can see that you can identify alpha decays because an alpha particle is produced as a product and you started with a heavy isotope and ended up with a slightly less heavy isotope. Beta decay, or beta emission, produces a beta particle. And as a reminder, this is how we write a beta particle, either as an electron or with the Greek letter beta. And in beta decay, a neutron in the nucleus is converted into a proton and an electron, a high energy electron that's ejected from the nucleus. So the nucleus, as a result, gains a proton, but the mass does not change. So look at how we can identify beta decay. These beta particles are produced at the end of the nuclear reaction. Whatever isotope we start with, we end up with an element with the same mass, but it does become a different element because the atomic number has increased by 1. In positron emission, a positron particle is emitted in the nuclear reaction. And remember what positrons are. This particle is emitted when a proton is converted into a neutron, and a positron is released as a high energy particle that's ejected from the nucleus. The result of this positron being emitted is that the nucleus loses a proton, but the overall mass does not change. So here's an example from a nuclear reaction. Oxygen 15 releases a positron, and the resulting element still has the same mass of 15, but the number of protons, the atomic number, has gone down by 1. And so we now have nitrogen. There is another type of nuclear reaction that involves beta particles, and that is beta capture. This is when a beta particle is actually a reactant, not a product of the nuclear reaction. So this is when an electron combines with a proton to form a neutron. And one example of this happening would be potassium with a mass of 40, kind of gaining an electron inside of its nucleus, converting a proton into a neutron, and therefore losing one of those protons. The atomic number goes down, and that changes the element, converting it to argon. But the mass has not changed. The mass is still 40. Notice here that this has a beta particle, but it's before the arrow, which makes it a reactant, not a product. Gamma radiation is a high energy photon. It has no mass, and it does not have any effect on the number of protons in the atom. And so this is often occurring with other types of radiation, where just kind of high energy is being released from the atom. So here we have tactinium, and it has a mass of 99. That M there is just an indication that for whatever reason this particular isotope is unstable. And at the end of this reaction, we still have a mass of 99. We still have tactinium because the atomic number is still 43. But we have given off gamma radiation in the process. So again, gamma decay or gamma emission releases gamma particles. Fusion and fission are important for in man-made uses, although fusion is extra important in the universe, in stars. So fusion is when two things combine to become one. Fission is when one thing splits into two or more pieces. In the case of fusion and fission, and these are nuclear reactions, so we're talking about two nuclei becoming one nucleus in the case of fusion, or one larger nucleus splitting into two or more smaller nuclei in the case of fission. So I did just say that. Fusion is when two light nuclei fuse together. This is an extremely high energy nuclear reaction. And this type of nuclear reaction does occur naturally, not typically human-induced, because this is the nuclear reaction that occurs in the sun and in other stars. So all of that energy that the sun releases, it is a result of fusion reactions inside the sun. And so here you can see helium is fusing together with hydrogen inside the sun to make a heavier version of helium, but is also releasing positrons in the process. We don't call this positron emission because the main focus of the reaction is two nuclei becoming one. Notice here that also this is not alpha emission. We do produce an alpha particle here. We produce a helium, but it is not considered alpha emission. It's considered fusion because we have two smaller nuclei becoming one. Fission, on the other hand, is when one heavy nucleus splits into two lighter nuclei. And typically this is human induced. It releases a large amount of energy, but not a very, very large amount of the energy the way the sun does or other stars. So it releases a large amount of energy, but this is human induced. And so this fission typically uses neutrons to get it started, and then may also emit neutrons as a product at the end of the reaction, which might then go on and stimulate other fission reactions to occur. So in this case, we are starting with uranium 235, and in a nuclear power plant, we might bombard it with neutrons to make the nucleus a little heavier, a little less stable, so that it decays when we want it to decay, because we're trying to produce electricity. Once we've made that nucleus unstable, it splits into two. It splits, in this case, into barium and krypton. But in the process of splitting into two smaller atoms, more neutrons are released. And then those neutrons can go off in different directions and bombard more uranium atoms and make them unstable and cause them to undergo fission. So this is a chain process. It needs to be controlled very carefully to make sure that it doesn't get out of control and release too much energy all at once, causing a nuclear meltdown. And so this type of reaction would be used in nuclear power plants. So this is a summary of all of those different types of nuclear reactions that we've just talked about. This is the same information that was on the previous slides. That's just all here in one table so that you can compare alpha decay with beta decay, with positron decay or positron emission, or electron capture, or gamma decay, or fission, or fusion. Given the information I gave you about the different types of particles that can be released by a nuclear reaction, you should be able to answer a question like this about a type of radiation that passes through some substances but is blocked by others. So let's look at this example. A mystery type of radiation passes through paper but is blocked by wood and lead. What types of nuclear reaction might be occurring? Like what types of particles might be being emitted by this nuclear reaction? Well, remember, paper is blocked by, alpha particles are blocked by paper and skin, but beta particles need to be can pass through paper but are blocked by wood or aluminum foil. And so certainly something like lead would definitely block a beta particle, as would wood. So this looks like an example of beta. It could be beta decay, or it could be positron emission. These could be positrons that are also released because beta particles and positrons are both would be blocked by wood and by lead. Gamma radiation would penetrate through wood, so it would not be stopped by wood. Same thing with X-rays, and same thing with neutrons. Neutrons would not be stopped by wood. So beta particles are the best example here. I hope this helped.